Hello, friend. My name is Derek Harder, and this video is kind of a continuation of the previous video that we were doing. So there we looked at some best practices for modern convolutional neural networks. So just as a reminder, these are some of the architectural principles, and we're going to be seeing an example of these by looking at this exception-like model in this video. So in general, a deep neural network, especially a convolutional network, should be organized into repeated blocks of layers, usually made of multiple convolution layers and a max pooling layer. The number of filters in your layer should increase as the size of the spatial feature map decreases. Okay, so we saw both of those patterns in all of the convolutional neural networks that we discussed. So we were just talking about introducing residual connections around blocks of layers helps you train deeper networks. It helps avoid vanishing gradients. And it can be beneficial to use layers that are known as batch normalization, usually after convolution layers. And also, a little controversy on this, but it can be beneficial to replace the regular convolutional layers with separable convolutional 2D layers, okay? So we're going to put that together in this video here to build a mini exception-like model. So the exception model, again, the author of our textbook was involved in this, I believe, has all these principles. So this model, we're going to demonstrate having residual connections using batch normalization and the dropping in, replacing the separable convolution layers. Okay, so for context also, we're using our same dogs versus cat problem that we used for the first time when we looked at a convolutional neural network. So you should be comparing the results we get here with the first one that we did from scratch. Okay, so again, we're going to train from scratch. So we're not using any pre-trained version that has the benefit of having a large number of images to have been trained on. So we want to compare if we train from scratch, but we add in these more modern best practices of residual connections and batch normalization, whether we can improve the performance or not. Okay, so let's get started. As a reminder, and we're going to have all the things that we talked about before. So we are going to use data augmentation. So we'll have a sequence of data augmentation processes that we do on our right after the inputs. So then let's just look at this code here. Can't quite get it all on, but this is actually going to build the exception-like model, the exception-like architecture that we're going to use for this example here. Okay, so we've got our data augmentation. So as usual, we are using the cats and dogs again. So those are 180 by 180 pixels color images with 3 color channels. That goes into an augmentation layer. We do have this scaling layer that we've been using that its only purpose is to take all the values from 0 to 255 and scale those from 0 to 1 for floats, which is what we really need as input. And then we start with the convolution layer, but then after that, we have this loop, okay? So notice what this loop does. So this is going to be building blocks where the first block is going to be trained to create like 32 features using convolutions, and then 64, 128, 256, 512, okay? So this mirrors what the original exception network did. So for each one of these blocks, so when it's like 32, we'll do a batch normalization, and then one of the separable convolution 2Ds, and then another batch normalization, another separable convolution, and then a max pooling. So both of these separable convolutions are, we are using some padding, so they don't actually change the size, but we don't use bias, right? So like we talked about, and we're going to put a residual connection around each of these, right? So that's why we saved the residual up here before we created these layers, okay? So we did the things that we talked about in the previous video. So no bias on these convolution layers. And we use the padding so they actually keep the same map size, but then the max pooling will downsample by 2. Then we use a 1-by-1 convolution with strides of 2 in order to take the residuals and get them into the same shape as the output that comes from going through these 2 convolution layers. And we're using the batch normalization, and each of these layers don't use bias, and we defer doing the ReLU activation until after the normalization. All right, so that happens for the 5 different blocks. Okay, and then at the end, like we talked about, we have this global averaging pool, but we basically take the final output, and we are doing just binary classification again. So the dogs versus cat is just a binary classification. So we have a single dense layer that takes all these inputs and learns the predictions for cat or dog here. All right. So let's create that model. We can see the summary, but again, this is complex enough with residual connections and things that it's a little bit hard to visualize. You can see the general structure. We go 180 by 180. So this comes down to 176 by 166 by 32, and it gets downsampled by the max pooling, so it goes down to 88s, 44s, and so on, till we get down to the end with our final dense layer. I skipped over the dropout. We're also still using dropout regularization as well on this model here. So let's look at the model graph here. So each of these blocks will look something like this here. So I'll maybe just show the first one. So coming in here from our original, 176 by 176 after our first convolution layer, this is really kind of our first block, right? And then this represents the residual layer going over here, right? So here are the same inputs. So we go through our 2 separable convolution layers and then a max pooling layer, and then this input over here we just put it by the 1-by-1 convolution, so we end up with something the same shape that we can combine together, and then that goes on for the next layer. And residuals are going over here, and we've got our sequence of convolutions and max pooling over here. Right, so that's in general what the exception architecture looks like, And again, we have the same pattern that we had before in terms of the shape of our maps and the number of features that are happening as we go through the layers. The only thing is we've added in all those other things that we talked about. So we've got our residual connections to help with gradient, vanishing gradients. We're using batch normalization now, and we're using these drop-in replacement for our convolution layers. Okay, so putting that together, so if you go back and look, this model has 718,000 trainable parameters. This is actually a bit smaller than the number of trainable parameters that we had in the first model from scratch that we did, but in the same ballpark. So we're ready to go ahead and try this out. So, we're just using our standard binary cross entropy since this is a binary classification problem. And as usual, we will checkpoint on the lowest validation loss so that we can use that to go back and evaluate the model that was trained here. So let's go ahead and fit this for 100 epochs and see what kind of performance that we get with this exception-like model here. So again, this will take some time to train, so I'll come back once we're done here. Okay, so once training is finished, let's go ahead and see what the results we got. So as usual, let's go ahead and look at the learning curve. So this was our simple binary classification. So we do have accuracy metrics that we can look at. So you should get similar results. If you run this, this again is another one that you might need GPU or else it'll be kind of painful. It'll take a while to run this exception network. Okay, but so, looking at this evidence here, we're not obviously getting to overfitting yet, although things are flattening out pretty much. Not to mention that it took quite a while, so loss seems to be still going down, but it's not going down very fast. We can look at our accuracy. So remember, we're comparing with our other by scratch model that achieved 80, maybe 83 or 4% at best, okay? So this is what our validation accuracy looks like. So let's go ahead and pull off the best model by validation loss that our checkpointer found and see what we get for a final evaluation here. So you should usually see, that was pretty low on the low end, you should usually see that this model on average will achieve about 90% test accuracy. So, you know, compare that to our other by scratch model, which was getting at most 83 or 84%. Okay, so you know, the bottom line on this is that these new features, these best practices for convolutional neural networks, which would include residual connections, batch normalization, and possibly using the piecewise, stepwise convolutions, do have a pretty big impact on the performance here. So it improved a lot over, you know, we were training on exactly the same small amount of data here to compare the model without these kind of new features we just discussed and with these new features. So, and we could probably improve this more, you know, so I'm not convinced that we've hit the best spot of training here. So if we train some more epochs, I mean, it does look like we're about at the right balance between underfitting and overfitting. So, all right, so that's it with this video. I hope that example of a convolutional network with these more modern features helps you understand kind of what's going on. You'll find these very common in sort of the current crop of people doing convolutional neural networks. They'll almost use all these things that we talked about by default in different things that they do. So that's it for this video. I hope you liked it, and I hope you stick with me and see me in the next one.